Lecture 5 for History of Math, and there was a homework problem that discusses spheres, and someone asked me about that in one of the Zoom problem sessions, so let me say a few words. You remember, how do you define a circle? You take 2 points in the plane, and the circle is, you call one of them the center, and the circle is all the points where the distance from the center to that point is the same. So forgive this drawing, but if this is R, if I take any other point on the circle, the distance from the center to this other point B is R. And if you have a point whose distance from the center is R, it's on the circle. So that's how you define a circle in 2 dimensions in a plane. And in a sphere, in 3 dimensions, you have the analogous situation. You take a point and you take a second point, and the sphere, and let's say the distance from O to A is R. So the sphere is everything in 3-dimensional space whose distance from the center is R. So it's hard to draw 3-dimensional objects, but that's what a sphere is. So here we have a circle of radius R, and here we have the sphere of radius R. Now, if you take a sphere and you intersect it with a plane, so here we have a plane, the intersection of the plane with the sphere is always a circle, right? So intersection of a plane and a sphere, well, there are actually 3 possibilities. The first is the plane doesn't touch the sphere at all, in which case the intersection is empty, there's nothing. The second case is the plane touches the sphere at just one point, it's tangent, and then you just have that one point. But the general case is the plane cuts the sphere at more than one point, and it cuts the sphere, and you get a circle, right? Because this is always, it's just the surface of the sphere we're looking at. It's not the solid sphere, just as the circle is not the solid circle, it's just the curve around the edge. So the intersection of a plane and a sphere is a circle. And if you cut the plane through the sphere very close to where it would be tangent, you get a small circle. And as you cut the plane through the sphere and the planes get closer and closer to the center, you get bigger circles. And in the sphere, what is called a great circle is the intersection of a plane passing through the origin, passing through the center of the sphere. So you have the sphere and a plane that cuts through the sphere and passes through the center is a great circle. And if you look at the Earth, if you think of the Earth, the planet Earth is a sphere, the equator is a great circle. And in fact, every circle of longitude How do you measure longitude on the sphere? It's a circle that passes through the north and the south poles. Every circle of longitude passing through the North Pole and the South Pole is a circle, is a great circle. Right? So that's what a great circle is. A great circle on a sphere is a circle that you get by intersecting the sphere with the plane passing through the origin. And again, if you think of the Earth as a sphere, the equator is a great circle. Any circle that goes through the north and the south poles is a great circle. Now, if you have your sphere with the center and you intersect the sphere with a line through the center, if you have a line that goes through the center of the sphere, it's going to intersect the sphere at 2 points. There are 2 points that intersect. The 2 points of intersection are called antipodal points. And the simplest example is on the Earth, the North Pole and the South Pole are antipodal points. And again, if you think of the North Pole and the South Pole, they're antipodal points, but they lie on many different great circles. Every circle of longitude passes through the North Pole and the South Pole. So there's not a unique great circle through any pair of antipodal points. There are infinitely many great circles through every pair of antipodal points. And imagine this. Here we have a sphere. Think of this as the Earth, let's say. Here's the North Pole. This is the equator. So a line on a sphere is a great circle. So that on the surface of a sphere, we define a line to be a great circle, or a segment. A line segment is just a segment of a great circle. So suppose I take 2 points on the equator, A and B, and I have the line joining A and B is just this arc of the great circle from A to B. And let's say I take the North Pole and I join those by lines, which are arcs of great circles. Now, this longitudinal circle and the equator, they intersect at a right angle. This longitudinal circle and the equator intersect at a right angle. And here, between these two great circles, there's some angle theta. So on the sphere, if you look at the triangle NAB, the angles of this triangle add up to how much? I have a right angle plus another right angle, that's pi over 2 radians, plus theta, that's pi plus theta, that's greater than pi. So here we have a geometry on the surface of a sphere where a line between 2 points is the arc of the great circle joining the 2 points. And you have triangles, and the sum of the interior angles of a triangle on the sphere is not pi. Here's an example where it's greater than pi. So this is an example of what you might call a non-Euclidean geometry. So the theorem in Euclidean geometry that the sum of the 3 interior angles of a circle is pi is false on a sphere. Not only that, on a sphere, if you take 2 lines, so what is a line? A great circle. So here is one great circle. Take another great circle, 2 lines. Well, any 2 great circles intersect at 2 points. So there are no, this is very important, there are no parallel lines on a sphere. A line is a great circle, and every 2 great circles intersect in 2 points, period. Right? There are no parallel lines, so you can't say through any line and any point not on the line, there's a parallel line. There simply are no parallel lines on a sphere. So this idea of spherical geometry, it gives you a hint of what non-Euclidean geometries can be like. Right? So the purpose of the last 3 problems on homework 2 is just to think about the sphere and the surface of a sphere and how the geometry on the surface of a sphere is different from the geometry on the surface of a plane. So that's something to think about. Okay. Any questions about this? Okay. All right. So this is the 3rd week of the semester, and we have a simple calendar for the semester. Every week we do another chapter. So in the 3rd week, we begin to study chapter 3, which is on Euclid and the infinitude of primes. That is the title of the chapter. Again, I remind you, this week and next week are funny weeks because Monday there is no school because of Lincoln's birthday, and next week there's no school on Monday because of President's Day or Washington's birthday. So our next class after today will be a week from today, and we'll continue with chapter 3 next Wednesday. So it's a very, 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 very good book that we use as our core text. And what we did in chapter 2, we studied some of the geometry in book 1 of Euclid's Elements. And we'd say a little bit in this chapter about the next books in Euclid's Elements. It's divided up into sections. We might call them chapters, but in Euclid, the classical terminology is books. Books 2 to 6 have more geometry. And Euclid proves some things that today we would prove algebraically, but Euclid did not have algebra. The Greeks didn't know any algebra. So here's an example of proposition 2.4. This means in book Roman numeral 2 of Euclid, this is the fourth proposition. And it says if a straight line be cut at random, so here's a straight line, A to B, and you cut it at random. So just you pick some random point C on that line. The square on the whole what is the square on the whole? That means the square on the whole line. So here's the line from A to B. And this is the square on the whole. Right? It says the square on the whole is equal to the squares on the segments so let's say here, this is one of the segments from C to B. So that's the square on this segment. And this is the square on this segment. I'm just drawing it like that. Is equal to the squares on the segments and twice the rectangles contained by the segments. So the rectangles contained by the segments. So here's one segment, and here the small pieces of the other segment. So this is a rectangle contained by the segments. And this is another rectangle contained by the segments. So what Euclid is saying is what you see in this picture. You take the line, you take a line segment, say AB, choose any point C on that segment. So you've divided this line segment into two pieces. We might say, using a little bit of algebra, let's say the length of this is A, the length of this is B, so the whole line segment has length A plus B. So this is the square whose side is B. This square has side A. And the blue rectangles are rectangles with sides A and B. And this theorem of proposition 2.4 of Euclid says the area of the square is the sum of the areas of the two small squares plus twice the area of the rectangle. Now we have a simple way of saying that, because we would say the area of the black square is b squared. The area of the red square is a squared. The area of the blue rectangle is AB. So 2 times the area of the blue rectangle is 2AB. And if you add, what do you get? The sum of the areas is a squared plus 2ab plus b squared, which in algebraic language would be written as a plus b quantity squared, which is the area of the original square. So in algebraic terms, what Euclid is proving is this algebraic identity, which you learn in algebra. A plus b quantity squared is a squared plus 2ab plus b squared. But Euclid did not have available algebraic language, algebraic technique, algebraic symbols. So he states it geometrically, and it's very beautiful geometrically. It says if you take any line segment, pick any point at random, so you've divided the line segment into 2 pieces, the square on the small piece plus the square on the bigger piece plus twice the area of the rectangle is the area of the whole square. So this geometrical picture algebraically is translated into this identity. And it's worth spending a minute or two to look at that, because it really is quite lovely. All right. Any questions about this? I hope when I'm going through this material, you're not seeing it for the first time, because you know what the reading is each week, and you should really read the chapter before the lectures, and it makes it much, much easier to understand and follow what's going on. It also gives you a chance to ask questions about anything you might find puzzling.
I have a small question.
Go ahead.
So, we notice how we divided the line AB by some arbitrary point C, right?
Correct.
So on the on the right side of the square, would we cut it like the same way how it
Well,
gives us the same length B?
so you start with the line segment AB,
Yeah.
right? And you build the square on AB,
Yes.
right? So if the line segment AB is divided into 2 pieces by the point C, you do the same thing on each side, right?
Okay.
Because the total length of each side is the same, it's a square. So if we call the side AB, if we say that it has length little a plus little b, the same is true for all 4 sides of the square.
Okay, I see it now. Thank you.
Right? Because we're building the square on the line capital AB. And yes. Any other questions? Okay. There's another result that we are going to need later about quadrilaterals inscribed in a circle. And to prove that result, we need what I think is proposition, it's something in book 3 of Euclid, maybe proposition 21, which is only mentioned but not proven, which says the following, not proven in our textbook. It says, if you have a circle and you take 2 points on the circle AB and take any other point C, you have what's called the inscribed angle ACB, right? It's ACB. So that's an angle. All 3 of the points A, B, and C are on the circle, and it cuts out a certain arc on the circle. So let's call this, let's say, theta for the moment. Theta is that angle. Now, I could take another point on the circle, anywhere, say here, D, and I could draw the line from D to A and D to B. So we have another inscribed angle, angle ADB. So these angles have the property that the vertices and the endpoints all are points on the circumference of the circle, and they cut out the same arc. And the theorem says that angle ACB equals angle ADB. No matter where you take this other point D. If I took D to be, for example, the point E here, and I looked at angle A and angle B, that's a third inscribed angle that cuts out the same arc on the circle. And all 3 of these angles, my picture is not very good, but all 3 of these angles are equal. So if I have inscribed angles ACB, ADB, and AEB, then they're equal angles. Angle ACB equals angle ADB equals angle AEB. It doesn't matter where you take the third point, the vertex of your angle. If you take any point on the circle and draw the angle with that point as the vertex going to the points A and B, if the angles cut out the same arc, the angles are equal. And one way to prove this is by another proposition in Euclid, which says the following. Let me draw a picture again. Here's, let's say, the center of the circle. Say, here I have A, here I have B. Suppose I take a point C, and I look at this inscribed angle, ABC. Call this theta. So here I have inscribed angle ACB, theta. From the center of the circle, let me draw the lines from the center to A and the center to B. And then we call this angle alpha. So I have the inscribed angle ACB and what is called a central angle, AOB. A central angle in a circle is a circle where the vertex is at the center and you have rays going to the circumference. And the theorem says, or the proposition says, that angle theta is half of angle alpha, or 2 theta equals alpha. So an inscribed angle is half the size of the corresponding central angle. Right? So if you have any inscribed angle, it's half of the central angle. And how can we prove that? Let's see. So one way to prove this is to do what is often done in geometry. You have to think of some clever auxiliary line to draw. So suppose I draw the line, the diameter that goes from C through the center. So I draw this diameter, let me call this point D. So draw the diameter COD. Now this is the center. So all radii are equal. OC equals OA, because they are radii of the circle. So let me not call this alpha. Let me call it phi, say just. These two radii are equal. So triangle COA or AOC is isosceles. Of course, you have two radii as sides. So this angle here and this angle here, let me call them alpha, are equal. And but also OC equals OB because they're radii. So triangle BOC is isosceles. So this angle beta equals this angle beta. Mm-hmm. Now, let me call this this angle here phi1, and this angle here phi2. So this angle phi1 is an exterior angle of triangle BOC, which means, and the theorem about exterior angles, once you have the parallel axiom, says an exterior angle of a triangle is equal to the sum of the two opposite interior angles. The interior angles opposite this exterior angle are both equal to beta. So theta 1 is 2 beta. Similarly, if this exterior angle phi 2 is an exterior angle of triangle AOC. So if this angle is phi 2, this implies phi 2 is 2 alpha. If you add, you get phi 1 plus phi 2 is 2 alpha plus 2 beta, which is 2 alpha plus beta, and phi 1 plus phi 2 is this angle AOB, the central angle. So this says the central angle is, and alpha plus beta is this angle AOC. So you have to look at this picture for a bit, but you see, we just proved that the central angle is twice the inscribed angle. So we just proved the following proposition. If you have A, B, C, and the center O.
Professor, can I see that page one more time?
Sure.
All right, thank you.
So this is just to summarize. The inscribed angle ACB is half of the central angle AOB. And what is a corollary of this? If you take any other inscribed angle that cuts out the same arc, well, this inscribed angle will also be half of the central angle. So angle ACB is half of angle AOB, which is equal to angle ADB, because the red angle and this angle, they cut out the same arc. So that's a proof that all inscribed angles in a triangle that cut out the same arc are equal. And that we need, again, you don't need to remember the proof of this, though it's nice to study, but we need that fact to prove Proposition 322, which says that the opposite angles of quadrilaterals and circles are equal to 2 right angles. So what is a quadrilateral in a circle? Let me use my $2.59 compass to draw a nice circle. And a quadrilateral inscribed in a circle is simply a quadrilateral whose 4 vertices are on the circle. So I'm just taking random points. A quadrilateral is a figure with 4 sides. So here is a quadrilateral, A, B, C, D. So this is a quadrilateral inscribed in a circle. And the proposition says that the opposite angles of a quadrilateral in a circle are equal to 2 right angles. So, for example, the angle DAB, that's one of the angles in this quadrilateral, and the opposite angle is the angle BCD. So angles DAB and DCB are opposite. They're one pair of opposite angles. And similarly, if I take angles ADC and ABC, these are also opposite. So the proposition says that angle A plus angle C add up to 2 right angles, and angle B plus angle D also add up to 2 right angles. Now, how do we prove this result? So the first step is to draw the diagonals of the quadrilateral. So let's draw the line from D to B. And the line from A to C. So we draw the diagonals AC and BD. And let's call this angle in here angle 1, and this angle here angle 2. So we have triangle ABD. And in this triangle, the sum of the angles in a triangle is 2 right angles, or pi. It's 2 right angles. So angle 1 plus angle 2 plus angle DAB add up to 2 right angles, because those are the angles in this triangle. In triangle ABD, the angles are 1, 2, and angle DAB. And let's see, let me label 2 other angles. Let me call this angle 3 and this angle 4. Now, inscribed angle 1 cuts the arc of the circle from A to D. If you look at angle 1, it cuts out this arc from A to D. And inscribed angle 3 cuts out the same arc. This is angle 3, and it cuts out the same blue arc. So therefore, angle 1 equals angle 3. This angle equals this angle. And angle 2 cuts out the arc AB. Here's angle 2. inscribed angle 2 cuts out the arc A to B. And inscribed angle 4 cuts out the same arc. Angle 2 cuts out the arc AB. Angle 4 cuts out the arc AB. So angle 2 equals angle 3. So 2 and 3 are equal. Sorry, angle 2 and angle 4. 2 and 4 are equal, and 1 and 3 are equal. So angle 1 equals angle 3. Angle 2 equals angle 4. So angle 1 plus angle 2 equals angle 1 plus, sorry, angle 1 plus angle 2 equals angle 3 plus angle 4, right? If 1 equals 3 and 2 equals 4, then angle 1 plus angle 2 equals angle 3 plus angle 4. And if I add angle A to that, that's equal to this plus angle A. But angle 3 and 4 add up to angle C. And angle A plus angle 1 plus angle 2 equals 2 right angles, which is our proof. So let me go through that again, because if you're not familiar with elementary plane geometry, these are the kinds of arguments that you have to learn how to do. So we use the preliminary facts that we use are the following. If you take any inscribed angle in a triangle, it's half of the corresponding central angle. But this implies that any two inscribed angles that cut out the same arc are equal. So to prove our theorem about quadrilaterals, we take a quadrilateral and we want to show that opposite angles add up to two right angles. So A and C are opposite angles. We want to show that A plus C equals two right angles. Now, if I draw the line from B to D and the line from A to C, that is, if I draw the two diagonals of the quadrilateral, on the top I see a triangle. It has angle A, angle 1, and angle 2. So angle A plus angle 1 plus angle 2 add up to two right angles. The sum of the interior angles of a triangle is two right angles. But if I look at angle 1, it's an inscribed angle that cuts out the arc AD. And if I look at angle 3, it's an inscribed angle that cuts out the same arc on the circle. So angle 1 equals angle 3. Similarly, if I look at the arc from A to B, angle 2 is an inscribed angle that cuts out that arc, and angle 4 is an inscribed angle that cuts out the same arc. So angle 2 equals angle 4. So if 1 equals 3 and 2 equals 4, then 1 plus 2 equals 3 plus 4. But angle 3 and angle 4 add up to angle C. So that says that angle 1 plus angle C, the sum of those two angles, is the same as the sum of the three angles in this triangle, BAD. And that's two right angles. And that's the proof. So again, all of these things take time and a quiet place to think, to master. And
Professor, what's this? After you wrote triangle ADB, angle 1 plus angle 2 plus angle DAB equals 2 right angle. What's this after that? What did you write
so
here?
this says that inscribed angle 1,
Okay.
that's angle 1, this little angle here, it's
Mhm.
inscribed and it cuts out the arc AD.
Okay.
And inscribed angle 3 cuts out the same arc. So therefore, inscribed angles are equal. So angle 1 equals angle 3. That's what that says.
Okay.
And the same argument, type of argument, shows that angle 2 and angle 4 are equal because they both cut out the same arc of the circle, the arc from A to B. So angle 2 equals angle 4. So 1 equals 3 and 2 equals 4. That's what's going on. There's some more geometry that's worth mentioning and mentioned in the text. So what is called a regular polygon. A polygon is a figure whose sides are straight lines. And a regular polygon is a polygon all of whose sides have the same length. So a regular triangle, a regular polygon is a polygon all of whose sides have the same length, or let's say all of whose sides are equal, and all of whose angles are equal. So a regular triangle is what we call an equilateral triangle. You have three sides all the same length and three angles all equal. Right? And if the angles are all equal, each angle is pi over 3 radians, or 60 degrees. That's a regular three-sided figure. What about four sides? So this is three sides. A three-sided polygon is a triangle. And a regular triangle is what we also call an equilateral triangle. All the sides and angles are equal. What is a four-sided polygon? It's a quadrilateral. I mean, that's a quadrilateral. This is also a quadrilateral. But a regular four-sided polygon is a square. In a square, all the angles are equal and all of the sides are equal. A rectangle has equal angles, but not equal sides. So a rectangle is not a regular polygon. A rhombus has equal sides, but not equal angles. So a rhombus is not a regular polygon. The only regular polygon with 4 sides is a square. And so forth. You can have a regular pentagon. You can have, there's a pentagon with all the sides and all the angles equal. There's a regular hexagon, which is very easy to construct. It has 6 sides and all the angles are equal. So these are what are called regular polygons, and they were of great interest in Greek geometry. In particular, there is the following problem in Euclid or in Greek geometry. Inscribe, or is it possible, say, can you inscribe the regular polygon with n sides in a circle? So if you have a circle, can you inscribe a regular triangle? So the answer to this question is yes, for a regular triangle where it says the number of sides is equal to 3. There's a way to inscribe a regular triangle. There's a way to inscribe a square in a circle. Right? You can inscribe a regular triangle in a circle. You can inscribe a square in a circle. It's much harder, but it's true that there is a way with this, and this always means in Greek geometry with straight edge and compass. You can inscribe a pentagon. Right? This is much harder, but it can be done. You can inscribe the hexagon. Right? So all of these figures can be inscribed in a pentagon, in a circle. Now you can also do the following. If the answer is yes for some number n, then the answer is also yes for 2n, because whenever you have a figure inscribed in a circle, you can bisect each of the sides, draw the line from the center through the side bisector, for example, in this case, and then you connect these lines. So from the pentagon, we've constructed a 10-sided figure. So you can always double the number of sides. Even for the simplest case, take the circle, bisect the sides, draw the line to the center, connect these 6 points by line segments, and now you have the hexagon. So you can always double the number of sides. You can also become clever. For example, suppose you have your circle and you inscribe a triangle, and then using one of the points as a vertex, you inscribe a pentagon. So if I call this, let's say A and B, and this, I'll call this A, B, and C, the arc from A to B is 1/5 of the circumference. The arc from A to C, that's part of a triangle, is 1/3 of the circumference. So what is the arc from B to C? The arc from B to C is what part of the circumference? A third minus a fifth. A third minus a fifth. A third minus a fifth is 2/15. So the arc from B to C is 2/15 of the circumference. If I draw the line segment from B to C and bisect it, and then draw the radius from the center through that bisection point, let's call this point D, then the arc from B to D is half of the arc from B to C. That's half of 2/15, that's 1/15. So I can construct, so I've constructed an arc which is 1/15 of the circumference of the circle. So I just repeat this periodically around the circle, and I have a figure with 15 sides described in the circle. So that's pretty good. So there are infinitely many n for which there is a straight edge and compass construction of the regular polygon with n sides inscribed in the circle.
Mister,
Yes.
Professor, I have a little curiosity. So, as I was reading and playing around with this concept, I realized that each point on the circumference is also a tangent line, can be also represented as a tangent line because
Correct.
tangent lines only intersect the circle once.
Yes.
So as I started to draw out the tangent lines, I saw that the inside of a shape, let's say it was like the triangle that we see right now, came out as like another triangle, but in like an opposite direction. It was kind of weird.
Correct. Yes. So that's a very, very nice observation. If at each point, let's see here, you have the inscribed sphere. If you construct the tangent lines at each of those points, you get a figure of the same shape, a regular square. You have a regular quadrilateral square with the circle. Instead of the square inscribed inside the circle, you now have the circle inscribed inside the square. And I think using no more geometry than we already have been talking about, you can actually prove that as a theorem. But that's a very nice observation. Yes. So for certain n, for infinitely many n, can construct or inscribe regular n-gon in a circle. Question, is it true for all n? So what has been missing so far are numbers like n equals 7 or 9 or 17. Right? So are these possible or impossible? And for 2,000 years, it was thought that the only regular polygons that could be inscribed in a circle are the ones from Euclid. And one of the great discoveries of a mathematician named Gauss in the 18th century was, yes, you can inscribe a 17 gong in a circle? Well, I should say not yes, can you, but yes, you can inscribe a 17 gong in a circle. So the answer is yes for n equals 15, but it turns out it's no for n equals 7. It's not possible to inscribe a 7-sided polygon, a regular 7-sided polygon in a circle. So Gauss was a teenager, obviously a precocious great mathematician, when he figured out a construction for the 17 gong in a circle. It took another 150 years until one can prove that the answer was no for a heptagon, and the figure with 7 sides. So for this, you need to know a lot of what we call modern abstract algebra. But this is a classical question in geometry that took 2,000 years to solve. What regular polygons can be inscribed in circles? And it's a very, very nice geometrical question. Okay. All right, there's a lot more geometry in Euclid that we have not discussed, and that we're not going to discuss, because there's another part of Euclid that is as important as the geometry, which is number theory. So number theory is the study of the integers. 1, 2, 3, 4, 5, and so forth, even just the positive integers. And you might think there's not too much you can say about the integers, but in fact there is, and this is in Euclid, beginning in book 7. And one of the questions Euclid was interested in is whether you can measure one number by a smaller number. So for example, suppose I take the number 6. So if I take a line segment, which is 6 units long, I can actually divide it up into 3 pieces of length 2. So 2 plus 2 plus 2 equals 6. So I've divided this line segment up. I've measured it, if you like, by pieces of length 2. It's equal to 3 pieces of length 2. In fact, I could also have divided it up differently. I could have taken two pieces of length 3. So I can divide the line segment up into this line segment of this, or if you like the number 6, it's measured, it's twice 3, or it's 3 times 2, right? Or in modern language, we would say 2 divides 6. 3 divides 6. And so we can somehow measure the number n by the number d if n is a certain integer multiple of d, if n is d times q for some q. Or another way of saying that is D divides N. Now, 1 divides N for every N, plus N is 1 times N. And N divides N for every N, plus N is N times 1. And sometimes these are the only numbers that divide M. So 1 and 7 divide the number 7, but no other number, no other number means positive integer, no other number divides 7. And in general, we say that the number P, the positive integer P, is prime if P is bigger than 1 and the only divisors of P are 1 and P. So 7 is prime, 5 is prime, 6 is not prime because 6 is divisible by 2. 33 is not prime because 33 is divisible by 3. We say that N is composite if N is bigger than 1 and not prime. So a prime number is a number bigger than 1 whose only divisors are itself and 1. A composite number is a number bigger than 1 that's not prime. And what about the number 1? Well, we say the number 1 is the number 1, period, and it's not prime and it's not composite. It's just the number 1. And what are the first prime numbers? 2, 3, 5, 7, 11, 13, 17, 19, 23. You'll notice after 2, every prime number has to be odd because every even number bigger than 2 is divisible by 2. So if we're looking for prime numbers, we only need to look for the odd ones. See, 31, 37, 41, 43, 47, 53. It's kind of fun looking for these things. 59, 61, 67. Yeah. Those are the prime numbers. And the prime numbers are like atoms in chemistry. Every molecule in chemistry is a collection of atoms. Right? So water is hydrogen plus oxygen. Salt is sodium plus chloride. And in arithmetic, every number n is a product of prime numbers. 10 is 2 times 5. 11 is 11, just a product of one number. 12 is 2 times 2 times 3. 13 is 13. 14 is 2 times 7. 15 is 3 times 5. 16 is 2 times 2 times 2 times 2. 17 is 17. 18 is 2 times 3 times 3. Every number that you look at is a product of prime numbers. And what is called the fundamental theorem of arithmetic says that every positive integer bigger than 1 is a product of prime numbers, and not just that, in a unique way up to order. What I mean by order is 6 is 2 times 3. It's also 3 times 2. So here's 6 as a product of prime numbers, and the only difference between these representations is the order in which I've written the primes. Like 105 is 3 times 5 times 7. It's 3 times 7 times 5. It's 5 times 3 times. There are lots of ways to rearrange it, right? 12 is 2 times 2 times 3. 2 times 3 times 2. 3 times 2 times 2. 12 is a product of the primes 2, another 2, and 3, and you can rearrange the order, but you can't change the primes that occur nor how many times they occur. So this is what is called the fundamental theorem of arithmetic. Every number is a product of primes in a unique way. And this is one of the most important things to teach children if you become a math teacher, because this is really a basic fact about the world. We say that D divides N if N is a multiple of D. N is DQ for some Q. Everything is an integer. So 7 divides 105 because 105 is 7 times 15. 7 does not divide 106. Right? There's no way you can write 106 as 7 times some integer. D is a common divisor of two numbers, M and N, if D divides M and D also divides N. So 2 is a common divisor of 12 and 42. Because 12 is 2 times 6, and 42 is 2 times 21. 3 is also a common divisor of 12 and 42. Because 12 is 3 times 4, and 42 is 3 times 14. 6 is a common divisor of 12 and 42, because 12 is 6 times 2, and 42 is 6 times 7. And in fact, 6 is the greatest common divisor of 12 and 42. Right? So if you look at all the numbers that divide 12 and 42, of course, every pair of numbers has a common divisor because 1 is a common divisor of it. 1 divides everything. But there might be other common divisors, and it's of interest often to look for the greatest common divisor of two numbers. And problem. Given positive integers, M and N, compute their greatest common divisor. sometimes abbreviated GCD, the greatest common divisor of two numbers. Now, if any of you has taken a computer science class where you learned how to write a computer program, doesn't matter what language you're using, a typical problem is write a computer program to compute the greatest common divisor of two integers. And it is an amazing fact that you will find such a computer program in Euclid. Of course, they didn't have computers in Euclid's time, but they still had the problem. And there is what is called the Euclidean algorithm. So an algorithm is just another word for a computer program, something where you're given a strategy, a method to calculate something where you don't have to think at all. You just do what you follow directions and you automatically get the answer. That's perfect for computers because computers don't think seriously. They follow instructions. So there's the so-called Euclidean algorithm to compute the GCD, greatest common divisors, of two positive integers. And it simply uses long division. So let me give the example that you will find in the text on page 69. Compute the greatest common divisor of 3,796 and 1,387, right? That's the problem. And just looking at these two numbers, it's not clear what the greatest common divisor might be. Like you can see, this is not even, so it can't be divisible by 2. Doesn't end in a 0 or a 5, so it can't be divisible by 5. You can check it's not divisible by 3. So the method is take the larger of the two numbers, 3796, and divide by the smaller one. So there's something called the division algorithm, which is just long division. If you have two numbers n and m, you can divide n by m, you get a quotient q and a remainder r, and the remainder r is always no bigger than what you're dividing by. So if you divide n by m, the remainder is less than m, it's between 0 and m minus 1. So that's long division, or the division algorithm. It's always, they're unique numbers, a quotient and remainder that satisfy this. So if you divide 3796 by 1387, you get a quotient of 2 and a remainder of 1022. So you can check the arithmetic at home. Again, you should also look at the book where everything is legible. It's on page 69. Then you take this number 1387 and you divide by your remainder. 1387, if you divide by 1022, that clearly goes one time, and it leaves a remainder of
365.
Oh, this is a 7, 365. Okay, then you take 1022, divide it by 365. This goes two times and leaves a remainder
292.
292. Then you take 365, divide it by 292, that goes once and leaves a remainder
73.
of, oops, what did I write? 73. Then you take your 292, divided by 73,
Times
that
4
goes 4 times and
plus
leaves a remainder of 0. And the last positive remainder, 73, is the greatest common divisor of your two numbers. So the GCD of 1396 and 1387 is 73. Let's just check
Okay,
this is a,
Professor, it, yeah.
yes, sorry,
Uh,
go ahead.
It's 3796. It's not 1396. The GCD of you wrote 1396. It's
Oh,
37.
sorry, 1387, thank you.
No, it's 1396.
Hmm?
No, no. It's
3796
yes, 3796.
and 1387.
Yes.
Let's just check that this is a divisor. So if I divide 73 into 3796, this goes, I think, 5 times 15, 36, 4, 1, bring down the 6, 2. So this 3796 is 73 times 52.
52.
If I divide 73 into 1387, this goes once, and this into
19.
this goes 9 times.
It's 19, yeah.
Exactly. So 1387 is 9 times 73. 3796 is 15 times 73. And these two numbers have no common factor. So this is, in fact, the greatest common divisor. And in the homework on chapter 3, I will give you a number of problems to calculate the greatest common divisor of two numbers by the Euclidean algorithm, because this is really a fantastic thing. And as a computer program, if you study computer science, one of the main jobs of a computer scientist is not just to write a computer program, but to calculate how quickly the computer program will run, how fast is the program, how efficient is the program. And the Euclidean algorithm is an extraordinarily efficient algorithm. You can do better than that, but that's a fairly recent discovery. But the Euclidean algorithm itself calculates greatest common divisors very, very quickly. And typically in a computer programming class, one of the first problems you will be given is to write a computer program to implement the Euclidean algorithm. It really is quite nice. Okay. Let me say what we're going to prove in our next class, which is next Wednesday, which is the great theorem in this chapter. I had calculated a few minutes ago the first few prime numbers, and it's natural to ask, how does the sequence of primes grow? If you start looking at primes, like, I mean, here there are a lot of primes between 2 and 67. But if you go, let's say, from 1 million to 2 million, there aren't that many primes. If you go from 100 million to 100 million plus 1 million, there are even fewer primes. And it's quite likely, it's quite reasonable to think that at some point, there are no more primes. You've run out of all the primes. And the great theorem in Euclid in this chapter is that the opposite is true. There are infinitely many prime numbers. So if you keep looking for primes, you'll never get to the end. No matter how far you go, there's always another prime even bigger than however far you went. Right? The number of primes is infinite. So view that pi of x be the number of primes up to x. As x gets large, this goes to infinity. The number of primes up to x increases without limit. And some of the most famous unsolved problems in mathematics have to do with trying to find primes. And that is what we will talk about next Wednesday. So again, we have a week-long break. But this is, every chapter in this book is good. This is a very good chapter, and this material on number theory is really worth studying and absorbing. Any questions before we quit for the morning?
So for next week, we have a class on Thursday, right?
Let me just double check.
Thursdays and Mondays.
There is a makeup because of the Mondays that we missed. Yes, so next week, there are classes not on Monday, but a Wednesday as usual, and Thursday, February 22nd, we follow a Monday schedule, I guess. So next week we have 2 classes, but Wednesday and Thursday. That's right. Okay. Okay. Enjoy your Valentine's Day and see you next Wednesday.
I have a question.
Go ahead.
How do you get the quotients in the Euclid algorithm? Like 2, 1, 2, 1, 4. How did you get those?
Long division. You're just dividing, right? Remember, I said this, you can take any number and divide it by, take n divided by m, there's a quotient and a remainder. You get that by long division, which is, I don't know, where do they teach long division? 3rd grade, 4th grade, 5th grade? I don't know. But you just do long division, just divide. Right? I mean, there's some work involved, there's some calculation. If you're writing a computer program, of course, the computer does the calculation. If you're doing it by hand, you do the calculation by hand. It's just long division. Just the way right here, I did long division to divide 73 into 3,796. Just long division. Okay. If you need some practice with long division, I would just stop in at the Math Student Help Center in Gillette Hall, and they can help you. But that you have to know.
Why did you divide to get 2 in the 3rd row?
Here?
Yeah.
If you divide 365 into 1022, it goes 2 times with the quotient of 292, right? It's like 365 divided into 1022. That goes 2 times. 2 5s are 10, 2 6s are 12, 13, 7. This leaves a remainder of 2, 9, 2. So 1022 is 365 times 2 and a remainder of 292.
Okay. Thank you.
Sure. All right. Okay, be well all. See you next week.
Bye, Professor.
Bye.